Next, third one. Third one is we are finding the moment of inertia about a tangent also. About a tangent also. Suppose here what we have taken so far, this is a circular ring to be taken. This circular ring may rotate like this, or the circular ring may rotate about this diametrical axis like this, or this circular ring may rotate about the tangent. That a tangent can be taken as the two ways. Then one is the tangent here and another one is a tangent like this only. This tangent can be taken as this is the tangent which is along the plane or parallel to that plane, and this tangent is taken as the perpendicular to the plane. Now we are going to find out the moment of inertia about a tangent which is along the plane. So that's why I tangent is equal to, in this case, this tangent is parallel to the diametrical axis. That's why you can see two axes here, but you are going to find out the moment of inertia about this tangent only, not about this diametrical axis, about this tangent only. So that's why we apply the parallax theorem. So according to the parallax theorem, I tangent is equal to I dia plus mr square is here, and in this case I dia just now we got it, it is a mr square by 2, and after that plus capital M r square is here. Here that r is the distance of separation between these two axes, which is nothing but the radius of the ring only. So that's why this is the 3 by 2 mr square is here, 3 by 2 mr square. And thereafter we are coming to this fourth one is, that is the I tangent is here. This can be taken as the tangent which is normal to this plane of the ring. So that's why in this case what we are taking, that is the I diametrical axis plus mr square, means it is the mr square. So that's why it is a parallel to this INA plus mr square to be taken. INA plus mr square to be taken like this. So this is the axis, natural axis. This is the axis of rotation, and that circular ring is rotating like this now. In this case INA means already we know it is the mr square, and plus mr square is here, and this becomes the 2mr square. This becomes the 2mr square. In case of the circular disc also the same phenomenon that we can taken. That's why here also in the circular disc INA is equal to mr square by 2. But that INA for the disc mr square by 2 is not because of this either the parallax theorem or the perpendicular theorem. For that you have to take that integration process only, and it is taken as the mr square by 2. And thereafter again applying that perpendicular theorem, we can find out the I diametrical axis. So that's why in case of the disc, all this is for the ring, all this is for the circular ring, and in case of the disc, that is the INA is equal to mr square by 2, and again the I diametrical axis is the, so it is the mr square by 4 by applying that perpendicular theorem. And similarly you can find out the moment of inertia of that other two tangents also by applying that parallax theorem. So that's why so far we have completed the rigid body's uniform thin rod, and again the circular ring, and thereafter circular disc. And thereafter now we are coming to this, that is a solid cylinder. So how to find out the moment of inertia of the solid cylinder? So in case of the solid cylinder, how that natural axis is can be defined. So in case of the solid cylinder, natural axis means, now here it is a solid cylinder is taken like this. This is a solid cylinder. In this case now this is the axis is there, and that axis is parallel to the length, because it is the natural shape of that cylinder is this one only. And the axis, suppose it is nothing but a refill inside a pen. That natural axis is a refill inside a pen. So now in this case, now this is the axis of rotation, which is passing through the center and parallel to the length. So that's why this can be taken as the R, and again it is the L to be taken. And in this case, a solid cylinder, in the top view it appears to be a disc only. A solid cylinder in the top view it appears to be a disc only like this. So because of that reason what we are taking, that is the natural axis is INA is equal to, that is the mr square by 2, and this is the formula, this is the natural axis formula for the circular disc. The same formula to be used here also for the natural axis of that solid cylinder, because in the top view it appears to be a circular disc only. So that's why mr square by 2. And when you are coming to this, and the next one is the I equatorial axis. So first of all, we define that equatorial axis. Equatorial axis means it is an axis which is passing through the center and perpendicular to the length of that cylinder. Its meaning is that is the natural axis means it is rotating like this. That solid cylinder is rotating like this. Equatorial axis means it is rotating like this. Equatorial axis means it is rotating like this. This you call it is the equatorial axis, passing through the center and perpendicular to the length of that cylinder. So in this case, I equatorial axis means now when it is passing through the, suppose if at all this cylinder is considered a uniform thin rod, that naturally this becomes the natural axis, and which has the formula that is the ml square by 12. And similarly, suppose if at all you are considering the elementary section, any cross section of that cylinder is taken as the disc, and this axis is nothing but the diametrical axis which is passing to the center, means it is nothing but the diametrical axis of that disc. Diametrical axis of the disc means, that's why now it is taken as the, for the disc diametrical axis means mr square by 4. So that's why this is taken as the m of L square by 12 plus R square by 4. So both will be there. That is the m of L square by 12 plus R square by 4. So that's why as far as the solid cylinder is concerned, the main, that is the axis of rotation, are taken as the one is the natural axis and the second one is the equatorial axis. Natural axis means it is an axis passing through the center and parallel to the length like this. So that's why this is said to be the natural axis, just like a refill inside a pen. And equatorial axis means that is an axis passing through the center and again perpendicular to that. That is the equatorial axis means passing through the center and perpendicular to the length of that cylinder. That is said to be the equatorial axis. So it is the ml square by 12 plus mr square by 4. Once again I repeat you, this is nothing but the uniform thin rod. If you are considering this is the uniform thin rod, it is the natural axis. So that's why it has the ml square by 12. And similarly, if you are considering any cross section of the solid cylinder is a disc, now the axis which is passing like this, it is nothing but the diametrical axis of the disc. So that's why mr square by 4 is also coming. M of L square by 12 plus R square by 4. And the same when you are coming to this hollow cylinder. This is the solid cylinder to be taken. Now we are coming to this hollow cylinder. So in case of the hollow cylinder, now it is the first one to be taken as the INA. INA is taken as the mr square. Why? Because that hollow cylinder in a top view is considered to be a circular ring only. So that's why INA is equal to mr square to be taken. And similarly, when you are coming to this equatorial axis, that is the equatorial axis, it is the, as usual, that is ml square by 12 will be there. And this is the diametrical axis for that circular ring, which is nothing but the mr square. So that's why it is the mr square to be taken. M of that is the L square by, mr square by 2 to be taken. M of L square by 12 plus R square by 2 is there. Bigger one. So that is the m of L square by 12 plus R square by 2. So that is a solid cylinder and again the hollow cylinder. These are completed. So far, what we have completed, those rigid bodies are that is the uniform thin rod, and again next one is a circular ring and the circular disc and the solid cylinder and the hollow cylinder. So 5 rigid bodies are so far completed. Now we are coming to the next one is the rectangular lamina. We are coming to this next one is the rectangular lamina. So in case of the rectangular lamina, suppose if at all this is the rectangular lamina, what we can take like this. So this is the rectangular lamina is here. In this case, this is the rectangular lamina. So first what we this if you consider this is the rectangular lamina, in this case this is the axis, it may be rotating like this. That's why that axis is that can be taken as the I is equal to ml square by 12. Ml square by 12 means this is a perpendicular to the length. So this is the rectangular is here. That's why it is a perpendicular to the length. So that's why I is equal to ml square by 12 is taken. And this is a passing through the center and perpendicular to the length of that lamina. Length of that lamina, that is the ml square by 12 is here. Similarly, that may rotate like this also. Suppose a perpendicular to the length means it is rotating like this. And that is the, it may rotate like this also. In this case, it is perpendicular to the breadth. So that's why this also can be taken as the I is equal to mb square by 12. I is equal to mb square by 12. Its meaning is that is first one is it is passing through the center and perpendicular to the length ml square by 12. And the next one is passing through the center and perpendicular to the breadth, that is the mb square by 12. Now when these are taken as by using that perpendicular theorem, so perpendicular theorem INA, that is the perpendicular theorem, that's meaning is passing through the center and perpendicular to the plane of the lamina like this. Passing through the center and perpendicular to the plane of the lamina. In that case, INA is equal to, that is taken, x is here and again the IY is here, that can be taken as the ML square by 12 plus MB square by 12, and it is the M of L square by 12, L square plus B square by 12 to be taken like this. That is the INA. That is INA to be taken in case of the rectangular lamina. So rectangular lamina INA is equal to M of L square plus B square by 12, and there are, suppose if at all it is the square, if at all it is a square lamina, instead of that B you have to take the L only, and that becomes, it is the ML square by 6, that becomes. And there are so many number of axes of rotation in case of the lamina. Suppose it may rotate like this also about the diagonal also it may rotate. Suppose if you want to find out the moment of inertia about this diagonal for any square lamina like this, then you have to apply that perpendicular theorem, because one diagonal is said to be, that is the Ix, another diagonal is said to be the Iy, and this will be the Iz. Like that, about this for the square lamina you can find out the moment of inertia about this diagonal also. Now here, but that is for the square lamina only, not for the rectangular lamina, because the compulsory condition that Ix and Iy have to be mutually perpendicular. In rectangular lamina, that Ix and Iy cannot be the mutually perpendicular. So that's why for the square lamina we can find out the moment of inertia about the diagonal like this. Now, so we can see that also, that is the, after that, that is a solid sphere, that lamina is over, and after that, that is a solid sphere is there. So for the solid sphere, what we are taking in case of this, that is a solid sphere, and here it is the solid sphere is that, and I diametrical axis we are taking, and in case of the solid sphere, natural axis is nothing but the diametrical axis. INA is nothing but the diametrical axis. INA is equal to I dia, and that can be taken as the 2 by 5 mr square. 2 by 5 mr square. Here you have to remember one thing. The same diametrical axis cannot be the natural axis in case of the circular ring or the circular disc. That diametrical axis cannot be the natural axis in case of the circular ring and the circular disc. And here the diametrical axis becomes the natural axis in case of that is a solid sphere or the hollow sphere. In case of that solid sphere or the hollow sphere, only the difference is, in case of the circular ring and again the circular disc, we have that plane. That's why it is the perpendicular to the plane, that only becomes the natural axis. So here it is the diametrical axis can become the natural axis, that is the 2 by 5 mr square. In the problems also, generally you won't be mentioned the axis name. So the name of the axis may not be mentioned. It is given as the body is rotating about its natural axis, or rotating about its geometrical axis, or rotating about its own axis. In all these three cases, what we have to understand, it is nothing but the natural axis. It is nothing but the natural axis. If it is rotating about its geometrical axis, or the own axis, or the natural axis, directly it is given. It is the natural axis only that you have to apply that formula. So INA is equal to I dia is equal to 2 by 5 mr square, and similarly that is the I tangent is equal to, in that case, I tangent is equal to, now this is a sphere to be taken, and now it is the tangent means it will be like this. So that's why it is the I dia plus mr square. I dia plus mr square. So 2 by 5 mr square, and again the mr square to be taken. So it is a 7 by 5 mr square. That is the I tangent. Similarly, we can find out the that is for the hollow sphere also. This is for the solid sphere, hollow sphere also. For the hollow sphere, it will be the 2 by 3 mr square up there. And again, I tangent is equal to, that is again it is the 2 by 3 mr square plus mr square. That becomes the 5 by 3 mr square. So these are considered to be the important rigid bodies, and some of them are the rolling bodies also here. and these are the bodies about there are the so many different moments of inertia about the different axes are there. So far we are having almost more than 20. That is regarding that. Once I repeat all of them. So for the uniform thin rod we have that taken 2. That is the about the natural axis, and again that next one is about an end. And again for the circular ring and the circular disc, and 4 plus 4, that is a 10 already over. Next after that, when you are coming to the solid cylinder, that is a solid cylinder, there are the 2 we have taken about the natural axis, and the next one is about the equatorial axis. And similarly for the hollow cylinder, again the 2. So overall 14 are there. Overall 14. Suppose when you are coming to this rectangle lamina, you can have the moment of inertia about an axis perpendicular to the length and perpendicular to the breadth, and like this also about the natural axis, about an end also it may rotate like that. So that's why 4 or 5 formulae are coming there only. And thereafter for the solid sphere, again you are having the 2 formulae. And again for the hollow sphere, again you are having the 2 formulae. So more than 20 formulae are coming. Why that rotatory motion is considered to be the difficult chapter? Because number of formulae are involving in this chapter. Number of formulae, that too this chapter is the multi-constituent. So that's why that is a friction is involving, and again this that is a tensions, and again the pulleys, all these are involving like this. Now here it is the moment of inertia of the different rigid bodies in this class is over, and next class we are coming to that is the angular momentum, and again the conservation of angular momentum, and the velocity, acceleration, and the time taken for the rolling body when it is reaching that down the inclined plane. All that will be discussed in the next class.